Hello everybody. Today we are going to look at the PID controller and the model matching controller. This might be a recap due to the last week's session about the midterm, but here's still some detail to be delivered. Let's get right into it. Now, we have a second order transfer function, and we are asked to design a controller that meets the requirements of 10% overshoot and 2 seconds of settling time for the closed loop step response. Now we can see that we have 4 different tasks here. The first one being to design a PID controller using the tabulation method as usual. The second one is to propose a PID controller. Seems to be a different version of the first one. And then there's a task that says that we should propose a controller based on the previous designs, obviously. And then we will go ahead and design a controller using the model matching method. Now, let's first of all define our system transfer function, where we have 0.2, 20, 25.01. Now, this is a transfer function, but let's also define a symbolic version of it in order to be able to do some symbolic math. Plus 0.2 times s, 25.01. Now, we've defined them, and the first task is to design a PID controller. So, now, we've talked about this before, but let me remind you that if you are going to use the algebraic method, where we use the polynomial coefficients and their equality in order to get a solution or a design for the PID controller, then almost always you should go ahead and use the kp, ki, and kd parameters instead of zeros and the gain. And the reason behind that was that if you use kp, ki, and kd, you will get a polynomial that is linear in its coefficients, and that might help out in most cases because it's easier to process the information that you will have in front of you, and you can always go back and look at the zeros that are in our controller structure. Now we can define our controller that looks like this: kds square plus kp times s plus ki. And then, since we know the structure, it's a unique feedback structure, we can also look for the closed loop transfer function relation here. Now, if you simplify, we will see what this looks like. So, as I've told you before, you can see that the coefficients are linear. If you would have had defined it using the poles and zeros and the gains, k times s plus z1 times s plus z2, then you wouldn't be able to define these real coefficients, and you wouldn't be looking at the linear coefficient polynomial. So, now the step is as usual. We will go ahead and decompose it into its numerator and denominator polynomials. And we also know that the overshoot value is chosen to be 10% for the closed loop step response, and the settling time is 2 seconds. So based on that, I can define zeta, or I can calculate the value of zeta with this formula. This is the inverse formula. And I can also acquire the information of omega, the natural frequency that I'm looking for, because here what I'm trying to do is I'm trying to assign 2 dominant poles that have the following zeta and omega n values, and that will determine the dominant behavior of the closed loop step response. And I hope, most of the time that is the case, I hope that the other poles or zeros will be far left on the complex plane, so that I have a dominance there. So therefore I will need the settling time and overshoot parameters to provide me the corresponding zeta and omega n values, and based on that I can define my desired polynomial, desired characteristic polynomial, that looks like a second order polynomial. So I can see here that I have s cube in my closed loop characteristic polynomial. This tells me that I need a residue polynomial, or I need to somehow match the degree of the characteristic polynomial with my proposed polynomial. So that means that I have 1 degree to add. So again, I'm defining a pole here that is of course real, because I have 3 poles, so 2 of them can be complex conjugate. If I want to have real coefficients, the third one should be a real pole. Now my polynomial then looks like PDS times PES. So since the name implies the algebraic equation of polynomial coefficients and their equality, so I'm equating them, so I need to look for that information. So let us get the coefficients of the denominator of the closed loop, all the s coefficients that are available here, and the coefficients of my desired polynomial. So the problem then looks like the following. Then I have to equate PCS, the coefficients there, to Paul. Now let's take a look at them. Look at the problem. Now I have spotted a problem here. I can see that one of the equations is this here, and 100 equals 1 is a false statement. So why is that? This is because I have a gain in my system that causes the closed loop polynomial, the highest coefficient of that, to be equal to 100. And the way I'm proposing the polynomial is that I'm defining the poles and I'm multiplying that in a standard way. And I have s cube as the highest term. So in order to be able to equate these, I might get rid of this 100 here. So I can do that by using this here. If you look at PCS, you can see that PCS1 is equal to 100. So this means that I have to normalize this in a way so that I have 1 equals 1 here. This truth statement, this trivial statement here, or equation. Now, by dividing the whole polynomial by a coefficient wouldn't change the the positions of the poles or the roots of the polynomial, so I'm able to do this. Now, at this point I can see that K, P, Ki, and Kd, 3 parameters of the controller, and P in addition makes 4 unknowns, but I have 3 equations, since this is trivial here. This means that I have a free parameter and I have infinite amount of solutions to choose from. Now here it seems like it could be a good idea to use P as the free parameter and determine what Kp, Kd, Ki, and Kp will look like. We are able to do this by using the solve command in MATLAB, giving the problem, providing the problem, and we should also provide the parameters that we are after, namely Kp, Ki, and Kd. So if I do this, MATLAB or the sim engine behind the scenes will determine Kp, Ki, Kd in terms of P, because that's the free parameter here. Let's take a look at that. Maybe we might use VPA to get a readable result here. Ki and kd. Let's run this. Now I can see that this one is kp in terms of p, and this is 4p minus 13.56. So most of the time, since this is a PID controller, I'd like to have positive coefficients here. Or the coefficients should be the same sign. Since this is a second order polynomial, the polynomial of the zeros, or the polynomial that looks like kd times s squared plus kp times s plus ki. I'm talking about this polynomial here. All the coefficients being the same sign gives me two zeros on the left file plane. But this is violated if 4p minus 13.56 is not positive. I can see that p will be, if I choose p positive, which makes sense because s plus p is the residual polynomial, and if p is positive, I will have a stable closed loop system. If I have a instability in my closed loop system, that means that I am not able to design or use that controller because stability is the first condition here. So if I have a positive p, I can see that the value kd here, or the parameter kd, has positive values for all p positive. That's also the case for ki, but this can be violated because if p is positive and less than 13.56 divided by 4, then I might get negative values for this. So I should be careful about that. Now let's assign these to some variables. Let's say that this is kiv and this is kd. These are the placeholders that I'm going to use. There we go. Now the tabulation method is basically defining a table, and since I have a free parameter, changing the value of that parameter, I will be generating multiple results. So I'm keeping them in a table in order to look for the requirements, if they're met or if they're not. Or I will be looking at the optimality of my solutions and try to choose one of them. So this is basically gridding. I'm looking for an interval, and in this interval I will try every possible value, and I will look for the best result that is hopefully available to me. Now, since my free parameter is p, let's define a vector for p, and let's first of all start with 1 and 2. So two distinct values here. I'm going to increase that size, but since I'm trying to code, I'm trying to simplify stuff so that I will be debugging easier. So I will have to assign every row to every p-value. This means that the length of pvec will give me the amounts of rows that should be in this table. And then I will be storing some values. First of all, I should look for p, because that will determine the stability here. And then I have kp, ki, and kd, the controller parameters, or the PID parameters. And I like to use this order in kd, kp, and ki. The reason behind that is that I am defining kd, kp, ki in this order, and I can use this here directly to define the transfer function object in MATLAB. Now, since I have defined 4 unknowns here, which are defined due to the nature of the problem, I might also look for the values of the settling time and overshoot. Once I have a controller that is a solution here, I can plug that in to the structure, look for the closed loop transfer function, determine the step info, the information about the step response, and then I can store the settling time and overshoot in my table. So that will be the comparison here that I'm after, because I have defined the settling time and overshoot values here. If they're close, then I'm looking at a good solution, or a preferably good solution. Now, this makes 6 columns here. Each column is assigned to P, KD, KP, KI, TS, and overshoot. Now I'm going to loop in these in the predefined interval. The row will be defined as this here. Before that, I have placeholders and I know the value of P. So pval is equal to pvec I. So the ith element in this vector will be the p value that I'm trying to use in this solution. So then kpval will be calculated using the subs method here. I'm looking at kpv. I'm trying to plug in the value of p, and the value is pval. So this is the expression. This is the unknown, or the parameter that I'm trying to change the value of, and this will be the new value here. I will repeat this for kp, ki, and kd. Now at this stage, I know what the kp value is, the ki and kd value are. So this means that I can define my transfer function or my PID controller that looks like the following. kdval, kpval, and kival. So since the controller is defined, I can also use the feedback command here and look for the closed loop transfer function. Then, using step info, I can gather information about the step response. The TS val here, the settling time value, will be the following, and then the overshoot value can be acquired with line 43 here. So I guess I'm ready because I know what the 4 parameters here are. I know the values of them. I've calculated the settling time and overshoot values here. Let's fill the table. Now, you can of course use comma 1, comma 2, comma 3 and assign them individually, or you can provide a vector as I'm doing now. So kval, kdval. The ordering here is very important. If you mess that up, you will be looking at a problematic result, or a result that is not what you're looking at. There would be an error. Now, tsval and osval. So I'm basically copying this line here in terms of my parameters, and I'm filling the table here for each I iteration. I'm looking at the p value, I'm plugging in those values into my placeholders, or I'm determining what problem solution should be for that p value. And then I'm defining my PID controller. I have the system predefined, so I can look for the closed loop, get the step info, and then calculate or gather the settling time and overshoot values. Now at this point I'm ready. I can look at the table and see what it looks like. There we go. Now we have tried 1 and 2 for the p value here. Then I have kd here, which is positive, as I've told you before. I have kp, which is by the way negative, and this can be violated, as I've told you. Now ki is positive, and then I have settling time and overshoot values. Now I can increase this interval here like the following. I'm still not increasing it too much. Now I can see here that there are positive solutions and there are negative solutions, and I have corresponding settling time and overshoot values here. Now I've talked about this because kpv here, if p is positive, then this might be negative, but somewhere here it becomes positive, and then it will stay positive. So the roots of this for example, will show me the location of the possible zeros, and it gives me a complex conjugate left half plane 0 pair. Now, since I'm looking at the settling time and overshoot values, and since I've already defined them here, I might look at the error between the settling time here, for example, the absolute value of TS and TS val. I'm looking at the difference here, and I can also repeat this for the overshoot, but there's a slight problem because I want to combine them using a convex combination here. I will be trying to combine them equally, because the optimality of the solution in terms of settling time and overshoot are combined with the same weight here. Now the problem still remains because this is settling time and this is overshoot. I can't combine the values. If I do this, this will be not equally because I have to get rid of the second here, and this is percentage. So combining them is only possible if I'm looking at percentage error here. So if I divide it by the value that I'm looking after, this means that the error is now unitless. So this will be a percentage. And if I do the same for the overshoot here, I get two percentages. At this point, I'm looking at a combinable error here. So this is also a normalization. If it's a good solution, this should be 0. If it's, let's say, 100% off of my desired value, then I should get a 1 here. So if it's more than that, I get bigger values than 1, but they are already not very optimal. Now I've combined them, so maybe keeping track of this percentage error here is a good idea, since I'm going to try to use this as my objective here. Now let's look at the possible table here. Now these are the controller parameters, settling time and overshoot. Now here we have a metric that will help me in choosing a solution. For example, this solution looks very much optimal in terms of settling time and overshoot, because this is a lesser value than the others. Now, how can I get this row? Because this seems to be the optimal solution that I'm after. Now I can use so I'm looking through all the rows here, but I will be looking at the last column. So this means that a colon comma end gives me basically this column vector here. I will be looking at this, and I'm looking for the index where this is minimal. So I will be using val and index. You can look it up. The main function provides you the minimum value by default, but if you're looking at the index where this happens in your vector, you can get that too. And I'm not interested in the value because it doesn't make much sense. It's just to just for comparison. Now I can get the optimal solution in terms of the minimality of this column. So this will be the index row, and I will be looking at all the columns. At this point, this is my optimal row or solution. So there we go. I can see that I've acquired this. So this is not. This is up to you. You can also look it up and choose it by just visual inspection, but you can also just easily code this, so this will do its job on its own. Now I know what the p-value is. I can also get the controller parameters directly. This will be this one, this, and this. These three parameters are the controller parameters, and they are in order. So I can use them to define my transfer function, my PID controller here. So you can also take row 2, row 3, and row 4, and then define them as KP, KI, and KD values, and then use that instead. But you can also take a shortcut as I'm trying to do here. Now, at this point, I can copy and paste this line 40 here, because I will be looking at the closed loop again. And since while we're at it, let's look for tsval and osval here. So this is row, what is it again? Since this is 4, this is 5 settling time, and 6 is overshoot. Settling time and overshoot. So now we have also error here. Now I'm looking at an optimal solution. I will just look at the step response. Let's hold on and grid on. Let's also define this as an axis and get that. So we will use the step function to determine what the closed loop step response looks like, and then we can use plot x1 t, y, maybe a line width of 2, and maybe a color. Let's say this should be black. Now some label. This is time. And let's look at the title, which is the step response. You could also use step on its own, but I like to customize my plots here. And maybe a display name that shows some information about my settling time. Num to str tsval, and repeat this for overshoot, so we can see what the overshoot value looks like. Now, I guess we are ready. The only problem being the gridding interval is not that big, so we should maybe fix that. There we go. Now we have a step response accomplished. Maybe we should increase this here a little bit. Let's, for example, try 1 to 50 and look where the index is, so we can also determine which one is the solution that looks optimal here. Maybe we might look at pval or pvac, the index element here. We've looked up which row it is. That row also corresponds to pvac index. You can also use row 1, which is the same information because we've also kept that in our table, so works both ways. So we can see that the second solution here, or the solution where p is equal to 2, seems to be optimal. We can also inspect the table, and we can see that this is a kind of a high value. It becomes somewhere here we have a good solution, and here even a better one. So maybe gridding this interval might be more sensible to do. Let's try that. Let's take the interval 1, 4, but with a higher precision, 0.1, or maybe 0.1 with 0.1 steps here. Now again, this value looks pretty good. Let's also inspect that. We can see now it is somewhere around here. There's a good solution, and we are looking at that. So this one is the best one. We came up here, and now let's look at the step response here. We can also get rid of this. Let's look at the step response. We should maybe add this line here in order to see the time data here. Show the legend. We can also click just a button on the GUI here, but let's code it. So I can see that the settling time here is 2.1 seconds, which is pretty close. And then we have also almost no overshoot, 0.08. So it looks like a good solution in terms of the requirements, the time specifications, but in terms of the visual of the SAP response, we probably are not happy. If you're on a car that is accelerating with this profile here, you might get a little sick, because we are accelerating and then we slow down a little bit and then we try it again and then we reach our destination. Whereas we could have been just trying to increase it with a slower increment here, and we should not, or it is not that optimal in terms of the shape here. It is obvious why that is. So we may further inspect why this happens here. And in order to do that, a good hint could be hidden in the pole zero spread here, or pole zero map here. So let us just define a subplot. So side-by-side plots, one row and two columns, and the first one of them, let's clear the axis here, and this is defined like that. So if you were asking yourself why I was doing stuff with AX1 and AX2 here, well, basically this just updates that my code with minimal effort here. Now if I run one, I can see that updates directly reflect on that, so I don't have to adjust anything. So I'm going to look for my poles and zeros. I'm using a prefix here with the, because there's a zeros function, I don't want to override that. So pzmap of ts. Now let's use again plot. You can just use pzmap, but I like to customize stuff around because it seems to be the right thing to do in terms of customization. Now so I can plot these poles using the real values and imaginary values for the x-axis and y-axis. Now let's use black, and let's use a cross for that. AX2, by the way, this is the second one. And then I will be using the zeros here. And it should be a circle. Now the X label is the real part in the complex domain, and the Y label is the imaginary part. Title would be pole zero map. Since these are the properties of the second plot, I will be also providing this. Now let's look at the result. And there we go. Now we can see where my poles and zeros are positioned. But keep in mind that here we have also the origin, and we didn't it's not that clear to see. Maybe we could just use the values here, minus 0.25. Let's plot a line here that passes through minus 2.5 up to 0.5, and their y values should be 0 because this is the real axis, and then also the imaginary axis, maybe minus 3 up to 3. There we go. Now we can see where the origin is, and that the 0 pair here is on the right hand side. This is also not a dominant pole assignment. It's not dominant. I can see that because my third pole here is also in the dominant region. Now, this plot here explains the reason behind this interesting behavior here, because my zeros are on the right half plane, and it seems to be that these zeros are dominating the transient behavior. Although in the steady state I have the desired action here, the transients are a little bit off of my expectation. Now, this is the tabulation method because it is fairly straightforward. You're defining your controller structure, you have the unit feedback structure, or it might also be a not a unit feedback one, it could be any feedback structure. You're determining the closed loop transfer function in terms of the unknowns, and then you come up with a characteristic polynomial that is based on a second order polynomial and a residue polynomial that tries to equate the degrees of polynomials. And then we are looking at the coefficient equation problem. We're equating them and getting a result. If there's more unknowns than there are equations, then you might have infinite solutions. So you're looking at a spectrum of solutions. You're trying to use the most basic one here. You can also use different algorithms to come up with a good solution, but we are using the basic brute force approach here, kind of, and we are looking at the solutions one by one in a finite interval. Now we can see that this is the best we can get here using the tabulation method. Now the second task was to propose a PID controller. Let's maybe focus on that. Let's define it. Let's create a new script here. And at this point, we have to examine the system a little bit more. Now this is a second order system. It has two complex conjugate poles. And I can also look at the roots, what they are. But a way of designing a PID controller could be using the pole zero cancellation method. And that would be by choosing this polynomial as the zero polynomial of my controller structure. Now, therefore, I can just go ahead and look at my system transfer function that I've defined here. This would be my zero polynomial here. So, I know that if I'm using a PID controller, I am trying to choose two zeros, and I'm trying to place a pole at the origin, and I'm at that point updating the loop structure so that I have a different root locus than if I would have had a p-type controller. So by adding dynamic parts or the poles and zeros of the controller to the system, I'm updating the loop transfer function in a way that is desired in terms of the root locus plot. So at that point, once I have the optimal or the best possible root locus plot in front of me, then it would be easy to pick a gain so that my controller structure is fully known. And the strategy here is to use pole zero cancellation. Since there's a complex conjugate pair here, I cannot cancel the poles individually. I have to cancel them both at once. So this would be then the controller that I will be using. And let's look at the loop transfer function here. And let's look at the root locus of the given loop transfer function. Because I can use this to come up with a gain, because that's the only missing part here. And then I would get a controller. So what I'm showcasing here is that there's not only one way of designing a controller, there are also multiple ways in doing this. And as you can see, what I've done here is I've basically used the poles of the system. I've cancelled them with my zeros because my zeros are exactly on top of the poles of the system. Since I have a PID controller, naturally I've added a pole to the origin. And if I'm looking at this root locus, I can also see what ls looks like. Now this is the expression that I've got here, but you can see that there is a polynomial cancellation. Now if I use minreal, I can see that the minimal realization here, or if I'm cancelling out the poles and zeros, I can see that I have basically an integrator. So this explains why we have this root locus plot here. Now choosing a gain would give me the pole exactly at that position that I'm looking for. Now since the settling time requirement was equal to 2 seconds, and 4 divided by 2 gives me 2 because of the formula of the settling time, since zeta is equal to 1 in this case, I would get the desired time domain specification in terms of the settling time. So maybe I am not able to have any oscillations or any overshoot in my closed loop, but at least I can satisfy the settling time here, the criteria of settling time. So by choosing k equals 2, I think I would be getting what I want. So the controller that I'm proposing here looks like this. And it is interesting that I can do it in just one line, because I have not even coded anything. I have used the pole zero cancellation method here, and that's the only thing that I've used here. Now I can now borrow this part here and modify it a little bit so that I'm going to be able to compare my results here. So feedback, and then fs times gs comma 1. So at this point I'm looking at that. I don't need these parts here. Let's assign this a new color. Let's say this is blue. So I also need the step info here. Let's use this info equals step info, and then tsval should be equal to info dot settling time, and osval should be equal to info dot overshoot. There we go. Now I'm also looking at the poles and zeros. I'm changing them to blue. I don't need the axes or all the other stuff. Now let's run 1 and run 2 together because they depend on each other. There we go. Now we don't need this one. Now we can see that my behavior looks much better, because this would be the optimal way of accelerating, for example, or this would be the shape that I'm after. This behavior is not that optimal. So what is the reason behind that? Well, of course I have cancelled the poles with the 2 zeros that were available here. At that point I'm only left with just one pole that is on the real axis, and as I've done it earlier, I just have picked the value of 2 because I was looking at a pure integrator. So choosing this gain 2 here gave me the pole at -2, exactly at -2. So the settling time, as you can see here, is almost equal to 2, and this is very precise. But the only reason, or the only problem here, would be that my overshoot value is equal to 0, which was not the case that I was looking for. And I was looking at 10% overshoot. My other controller was also not that optimal in that case. So I have used the pole zero cancellation method, and I can also see that this is basically cancelling out. Now this is a known fact, basically. Here we are kind of implementing a filter that is the notch filter, a band stop filter, just because of the system itself. Now, we didn't look at the system's behavior, but if you look at it, if you look at the step response of the open loop system here, what you can see is we have high frequency oscillations here, and I can immediately see that my damping ratio is close to 0 because I'm close to the marginal stability here. And if you look at the pole 0 of the system, or the roots of this polynomial here, let's look at that. 1.2 and 25.1. We can see that we have a frequency of 5. If you calculate the zeta value, 2 times omega n times zeta, so if I have omega n equals 5, 0.2 divided by 2 makes 0.1, that divided by 5 gives me the zeta value of 0.02. So this is a low damping ratio. So this means that if this would have been a mass damper spring system, this would be less friction. So this means that I'm oscillating with a high frequency. Now what my filter structure in my controller does here, or this pole 0 cancellation corresponds to the band stop filter, notch filter. Now I don't have to choose them exactly at that point. I might also vary it a little bit in terms of the real value, in terms of frequency. I can also come up with a almost pole 0 cancellation, and this should also work, but it would mess up a little bit of the time characteristics of my closed loop. Let's run 1 and run 2. Now you can see that it does change it a little bit now, as you can see here, but it is a far better solution than the black line, the one before, and we can see that it almost matches my requirements. There is a possibility that my pole 0 cancellation passes through the right half plane, so it might end up in instability. So I should be careful about this, and I should be trying to place them so that there is no crossing, no boundary crossing. Other than that, the almost cancellation also works pretty well here in this case. So the only problem here is that if I'm insisting on my time domain requirements, the problem would be the overshoot here. So how can I overcome that, by the way? So now here task C gives me just the task of proposing any controller. Now of course this is not any controller. I know that I can cancel out the poles with my zeros, and I have a pole at the origin. Now if I want to modify my loop transfer function so that I can achieve some zeta values, maybe I might do something like adding another pole to my controller. Now let's try that. Let's open up a new script here. Now I was looking at the loop transfer function. Let me repeat that without any gain and any stuff here. So this times GS. And I was using another figure here and root locus ls. So now I can see that the pole 0 cancellation, or in this case I have an almost cancellation. Let me fix that too. I can see that I'm cancelling out the poles and zeros. If I would add a pole let's say at -4, then I would this root locus would pass through -2 here, because they would meet each other at exactly the middle of this line. So at that point, because of the real parts that I'm aiming here are equal to -2, I should add a pole at -4 so that they will meet each other and then will depart in different directions, or they would try to reach the asymptotes, 90 degrees in this case, because I have two poles. So then I would be able to draw a zeta line here, and it would cross this root locus, so I would get my solution somewhere here for 10% overshoot. So by just adding a pole to the 0 at exactly -4, 1 and 4, I would get the result that I'm looking for. So exactly here. Now, the only thing that is left is I should choose the zeta value so that my overshoot criteria is met, and it should be somewhere around here. So 11 point something, I guess, would be the appropriate value, but we could also look at that. Let's use minreal and look at our loop transfer function here, and it is equal to 1 divided by s squared plus 4s. So if I define a gain of k and define L as the loop transfer function using the symbolic variable, I would code something like this here. So the closed loop based on this loop transfer function is calculated using the following: k times ls plus 1 times k times ls. Now I would see that the numerator and denominator is decomposed, and I would get the denominator that looks like this: s squared plus 4s plus k. Now I know what PDS should be, so you can see that s squared, 4s, 4s, and then I have k, and then this value. So obviously k should be this division here. So before I go on, if you don't know where the position should be, you can also add it here. So you can say that k and p should be real, and then s squared or s times s plus p should be the loop transfer function. And then solving that could give you the answer. So you don't have to come up with the value 4 just by inspecting it. So the algebraic method could also provide you that you should add a pole at 4. Now, the problem is to calculate the coefficients of the denominator that I have here and the coefficients of PDS. So here I don't need any residue polynomial because I have a pole zero cancellation. This drops down the degree of the system. This reduces the degree of the closed loop because there's a cancellation inside. If that was not the case, we've seen that in the tabulation method that we had to add a pole, a residue pole. Now, let's look at the problem before we solve it, but it should be the same here. You can see this is satisfied, this is satisfied. So directly using solve, I should get the k value that I'm after. You can also use the root locus method or any method that would give you this here, but this is the minimal effort version that comes to my mind. Now at this point, I'm ready. I can use kval times. By the way, it would be a good idea to convert this into double. So kval times this structure here. There we go. I don't need this loop transfer function. So at this point, I will repeat run to here. I have the feedback and all this stuff. with a different color. Let's say this should be, let's make it red. So there we go. So I'm basically not changing anything. I could have also defined a function that would do this stuff here, but I'm okay with copy and pasting for the sake of simplicity. I guess we should be ready now. Now, if I run all the scripts that I've coded so far, I will get this comparison here. Now I don't need this anymore. I can see now, by the way, I might also go ahead and change the pole zero cancellation to exact here. I've updated that in order to be fair in the comparison. There we go. Now, obviously, I have 10% overshoot because I can see directly from here. And my solution looks just about right. Now, I can see that I have a pole zero cancellation here. Since they are cancelled out, these two poles, poles only are available and they are dominant. So this determines the zeta and omega values, and then those values correspond to the settling time and overshoot values that are given here. Keep in mind that the second order approximations work for a range of zeta values, and there are approximations, so there could be some errors as you can see here. But this control structure looks like is working as expected. Now, we have looked at the tabulation methods. We have looked at B and C here. The last part here is to design a controller using the model matching method, and the model matching method is quite related with our study today, because this time we come up with a desired closed loop transfer function. We know what the characteristic polynomial should look like if we are using dominant pole placement, so we might also construct, using this constructed closed loop transfer function, a candidate one that is based on this polynomial. And using that and not restricting the structure of the controller, but doing kind of a reverse engineering here, we would also be able to propose a controller. Now, I know that my closed loop should look like TSD here, and I know also, due to the structure, that my closed loop is something like this here. Fs times gs divided by 1 plus Fs times gs. Now, if I do the calculations, I would get this equation here. Now I can manipulate this further. I can multiply this parentheses here, and this would be the result. Now what I'm trying to do is I'm trying to get the controller structure that should assign my my pole zeros so that I have the desired closed loop. Now, since I'm looking for Fs, because this is unknown, because I'm reversing stuff around here, I can see that this would lead to the following. We have Fs times gs minus this here. Now, I can also see that further I can get this here, because there were they both had gs in them, so I can work my way out here so that this is equal to TSD divided by this whole here. So I've shown you the steps. I know what PDS looks like, or I know the values of zeta and omega. So let's come up with a closed loop transfer function. Now, of course, I know that the denominator should look like 2 times zeta times omega n and omega n squared, because the dominant pole placement is after this fact. Since I want to track step type inputs, I might also adjust the DC gain of the system, since if you're using the final value theorem, if you plug in s equals 0, we will end up with omega n squared in the denominator, and if I place the same in the numerator, they will cancel each other out and the DC gain would be equal to 1. Now I have defined my desired closed loop. I have also the relation because of the model matching here, and the reason behind that is that my controller has the inverse of the system, or I am cancelling sort of the poles of the system and the zeros of the system with zeros and poles of the controller. So there's a bunch of cancellations that get rid of all the poles and zeros of the system, and then I'm placing basically the loop structure that would give, or that would result in, my desired closed loop. If you look at TST divided by 1 minus TST, this would give you the loop transfer function. So we could say that the controller using the model matching method would give me LS and then divide by GS, since we're in single input, single output systems. I can write this. Now I can see that I'm placing the desired loop transfer function here, and then I'm getting rid of the system. And if you multiply by GS, you can see that this will end up in the desired loop structure, and then LS divided by 1 plus LS gives you the desired closed loop. So basically this should work. I can see that. Now let's look at the controller, the resulting controller here. Now it seems complicated, but if we use minreal first, because there are cancellations that we didn't get rid of. Now let's look at the structure of our controller. Now interestingly, we can see that the model matching controller gives us the same result that we had in run 3 or in task C. We have s and s plus 4. Now s squared plus 0.2 s plus 25.01 divided by s is the PID controller that we came up with. This was the denominator of the system. We were getting rid of this. We were using pole zero cancellation. The PID controller itself had s in it, so this was the part where we were defining the PID controller. And then we came up with this gain here. Then we've modified our strategy in order to match the zeta value here, because we were restricted on the real axis to the real axis. We have added the pole at -4 so that they would meet each other. These two poles in the loop transfer function would meet each other at -2, and they would then approach their asymptotes 90 degrees at that point. And since we were looking for the zeta times omega n multiplication to be equal to 2, the middle point of these would be giving us 2, which also would lead to the settling time of 2 seconds. Then we were choosing zeta so that it would give us the desired zeta value, and that was accomplished with using this gain value here. Interestingly, using the model matching controller for this system, in this special case, gave us the same controller here. Now, this actually tells us that using the model matching controller, or combining the good stuff in the PID controller design and the model matching controller design, we could come up with good strategies to control systems. And if there's an optimal controller for this system, several ways or different methods would lead us to that optimal result here. Now, I have also prepared a PDF, a solution manual for my PDF. You can see that I am explaining it line by line. So we have the overshoot criteria. Let's define this. minus log e, because in MATLAB we are using only log, but the log corresponds to the natural log basically. So this is basically the zeta value that we're after, and then using the settling time here, we can work our way out so that we can get a result where omega n is equal to 3.38. Based on zeta and omega n, we are defining the desired polynomial, and then we are defining our controller here, the structure, the closed loop structure, fs times gs divided by 1 plus fsgs. If we use the structure, since we are using symbolic math toolbox in MATLAB, we get this result. And constructing our problem step by step, we get this here. I have used a different method here, which leads to the same result. Only the difference here is that we construct our problem so that we don't have to use the solve method. We can use the inversion of the matrix defined here so that it would give us the result, the parametric result. I've used P in this video. You might also use KI, you might use anything else. After this, we can see that we have these columns here, and then we have these columns. If you combine them together and then get this formulation, you can look it up, gives you this parametric solution, and then we're starting to code our way to this tabulation. So this is not that necessary, just I wanted to just point out that this is also possible to use. You can also go ahead and use that. And the table that you're constructing may vary. You might look for K, P, KD, KI, and then the zeros, or you can use it, you can do the stuff that we've done in this video. Now we can see that this is basically the tabulation result here. We get this root locus looking at the loop function here. And then method B, where we use the pole zero cancellation, we get this result here. We've covered that already. And by adding just one pole at -4, we can use this here. If this is an approximate cancellation, it also works. You can see that this cancellation is almost done, and you can just approximate it like this, like a singular closed loop transfer function. The model matching method, you can see that I have explained it, I've tried to explain it step by step as shown here, and we get the result that we are looking for. Now, this basically concludes our lesson today. Hope that it was explanatory and it helped out in trying to understand basic aspects about pole zero cancellation, model matching, and hopefully also PID controller design. So, see you in the upcoming lessons, and have a nice day.